So, hello everyone again and welcome to this particular video, the Dajo Merit channel, where we're going to dive into calorimetry, problem solving question. And in here we have a question that states that a 248 gram piece of copper is actually dropped into a 390 milliliters of water at a specific temperature, which is the starting temperature of water to be around 22.6 degrees Celsius. Now, the final temperature of water was measured as 39.9 degrees Celsius, and in here, this question is asking us to determine the initial temperature of the piece of copper. Now, assuming that all heat transfer occurs between only copper and water. So in a calorimeter we have a specific device that actually prevents heat loss to the surrounding and keeping the heat actually trapped in a specific container that actually keeps heat contained in there, and we actually notice this to actually be effective in terms of not only constructions that you might explore in your last years of high school, but also a little bit in your first year of undergrad. But diving into this, we have usually a thermometer, we have a stirrer, and we have a cup. And this cup can either be a styrofoam cup for just generic purpose or something quite sophisticated. So in here we have water in there, and water at, I would say, normal temperatures. When there is no heat injected, the temperature remains the same. However, we put something that is quite hot, like for example a piece of copper, and what happens is that copper, once added in water, actually passes its energy into water, thereby increasing the temperature of water. And of course, if heat is lost by copper, we know in this case that the temperature of copper inside the water surrounding will actually drop. So in this case, it will drop to the final temperature of water because they are establishing thermal equilibrium. So once you're able to actually have this mentality at the back of your mind, we can actually get couple of information from external sources, like for example the specific heat capacity of copper to be around 0.385 joules per gram degree Celsius, and that of water to be around 4.184 joules per gram degrees Celsius. Now, since you're able to get the givens in the question, which is the mass of copper, the mass of water, we have the final temperature of water to be around 39.9 degrees Celsius, and we have the initial temperature of water to be around 22.6 degrees Celsius. By default, for the final temperature of water, that should be the same as the final temperature of copper. Now, looking at the mass of water, which is in terms of volume, milliliters, we know that the density of water is around 1 gram per milliliter. So by doing the conversion, we know that that particular volume is equal to the mass in grams of water. So using a specific formula that is mainly targeted towards calorimetry to be the sum of the heat gain and loss is actually equal to 0 in a specific system, we know that the heat of copper plus the heat of water equals to 0. Thereby, if you move water to the other side of the equation, we have a negative sign, where in this case we have that the heat loss or gain by copper is equal to the heat gain or loss by water. So in this case, we notice that the negative sign is not an arithmetic indication in a way. It just actually is a sign that indicates both quantities are opposite in direction of heat flow, either gain or loss. So in this case, once you know that the heat is actually related to the mass and the specific heat capacity and the temperature change of both materials, which is copper, and on the other side of the equation, which is water, we actually put our variables in there where we actually indicate both the initial temperature and final temperature of copper alongside that of water respectively at the other side of the equation. If you see the negative sign in here, we can actually do both sides. We can try to see if we put the negative sign on the left side of the equation, what will happen. We will notice that once you put in your values, it only changes the number that has a coefficient in there, making the positive sign right there of 95.48 times initial temperature, and that minus 3,809.65, while this is actually equal to 28,202.48. And then when you actually move the 3,809.65 to the other side of the equation, what we get is the sum on the right side of the equation, which results in 32,012.11. and then when you actually divide both sides by 95.48, what we get is the initial temperature to be 335.28 degrees Celsius. Now, if you try this, for example, looking at it on the other side of the equation by actually putting the negative sign on the other side of the equation, what we see is that we have two negative signs where you move the 3,809.65 to the other side of the equation, so you have negative 28,202.46 minus 3,809.65, and that value will give us negative 32,012.11, and this in this case is equal to negative 95.4 times the initial temperature. So if we divide both sides by negative 95.48, what we get is our final answer to be 335.28 degrees Celsius for the initial temperature. So this actually shows that no matter where you move the negative signs, either on the left side of the equation or the right side of the equation, we get the same answer, and you must always put a negative sign in one side of the equation. Don't remove or forget to put the negative sign, otherwise you will not establish the main idea, which is one material must gain and the other material must lose heat. So that's about it for calorimetry and this application question. Please hit the comment down below. Let me hear your thought about this. By that way, I can talk to you all in the comment section. And be smart, believe in yourself, and see you on my next video. Stay smart.